Hello, I'm Nick Fishman, and today I'm going to be discussing my paper written with Leif Hancox-Li, Should Attention Be All We Need? The Epistemic and Ethical Implications of Unification in Machine Learning. Before we begin, it is worth clarifying what we mean by unification. We take unification to encapsulate trends toward fewer types of models being used across more diverse domains and tasks. There are two particular waves of unification in machine learning research which we take to be paradigmatic. First, the rise of neural networks and the concordant dominance of end-to-end learning, and second, the more recent advent of transformers. Before the current wave of unification behind transformers, we had the spread of neural nets and end-to-end learning as popularized by Andrew Ng. End-to-end learning removed the need for feature engineering and its attendant domain expertise. Instead, neural nets, which were capable of being trained on so-called raw data, became popular. Later, in a seminal paper titled Attention is All You Need, the seed for transformers dominating multiple natural language processing tasks was sown. In a few years, their success spread beyond NLP. Transformers now dominate leaderboards on benchmarks for multiple tasks across different domains. This trend has led to some machine learning researchers expressing excitement over the prospects of what we call unification in machine learning. The idea is that fewer model architectures are being used across more tasks and domains in machine learning, with fine-tuning features or models being less necessary. Here we present an example of this excitement from the then director of AI at Tesla. He expresses excitement that researchers in one subfield of ML, say computer vision, can now more easily understand papers in other subfields like NLP. Other benefits he points to include the rapid propagation of improvements in one model to other parts of AI, the speeding up of progress, and the possible connection to the neocortex's allegedly uniform architecture. We snapshot these tweets because they hit on a lot of points that others make in favor of unification, but we emphasize that we have found similar expressions of excitement in many other venues, including industry retrospectives, blog posts, podcasts, and so on. These views on unification tend not to be explicitly expressed in ML research papers, but are a driving underlying ideology in the field. Our main research question is as follows. Is the excitement around unification in machine learning justified? What actual epistemic benefits are there? What epistemic risks have not been considered? Are there also attendant ethical benefits and risks? We will now discuss whether the epistemic benefits that proponents of unification hint at can survive scrutiny from the perspective of philosophy of science. The short answer is that most of them are not epistemic benefits unless we accept some dubious assumptions. We start with ontological unification. One reason to be excited about unification under transformers or any other model architecture is if you think such unification is pushing towards a unified understanding of general intelligence. This type of unification is common in the natural sciences. Many key advances in science occur by showing that some common structure underlies diverse phenomena. Examples of this include the Standard Model in physics and the theory of evolution in biology. These unified theories have uncontroversially been epistemically beneficial. Some such motivation likely underlies the excitement around unification in machine learning. The dominant ontological explanation for the success of neural networks is biological, as hinted at by Karpathy's mention of the human neocortex in relation to transformers. If all the best models have the same architecture, and this architecture is similar to the human brain, then maybe we would have solved the mystery of intelligence. We don't think this line of thinking around ontological unification is a good reason to embrace unification in ML research as it's currently manifested. Even if transformers are indeed the best performing neural network architecture, they are still based on multiple biologically implausible assumptions. To name just a few, like most modern artificial neural networks, they assume non-locality in neural communication. They are also, unlike biological neural networks, not spike-based. These are problems with most modern neural network architectures. The prospects of ontological unification are at the very least doubtful, given these dominant dissimilarities. This doesn't mean that research on these artificial neural networks is irrelevant to biology. Some researchers have made careful analogies from the artificial case to the biological case, but this requires caution in the construction. We just want to make the point that unifying all ML models to be transformers is not, on current biological knowledge, the best route to take if ontological unification with respect to the human brain is the goal. Indeed, ML practitioners have tended to err on the pragmatic side, proceeding with the model architectures that perform the best on benchmark, regardless of biological plausibility. For these reasons, we do not think ontological unification is a particularly good reason to pursue the current wave of unification. It is possible, though, that some future wave of unification would be a better candidate for this epistemic benefit. We now turn to another class of possible epistemic benefits from unification in machine learning. These are benefits coming from explanatory unification. The idea, roughly, is that it is desirable to have one explanation for many phenomena, rather than to have to give a separate explanation for each phenomenon. Classic examples of explanatory unification in science are with physicists' unification of 3 of the 4 fundamental forces, and the way the modern synthesis in biology can give evolutionary explanation for a wide variety of biological phenomena. In the next few slides, we'll discuss some ways in which unification in ML could be a kind of explanatory unification. One obvious way in which unification in ML may be explanatory is if such unification helps us explain any similarities between artificial and human intelligence. However, ML would be explanatory in this way only if the unified architecture in question is ontologically similar to the brain. As we argued earlier, we do not think that modern neural networks are biologically plausible, so for now, we think researchers should not give too much weight to this type of explanatory unification. A second type of explanatory unification that can happen is if ML unification helps us understand the so-called inductive biases that underlie the success of today's ML models. Machine learning researchers use the term inductive biases to refer to preferences for the types of functions that the model represents. Inductive biases are thought to be necessary for models to generalize to new data. Unified models provide an opportunity for us to understand the shared inductive biases latent within many neural networks. Since they are successful across more domains and tasks, we can potentially find in unified models the basis for common explanation behind the inductive biases of a diversity of domain-specific models. Unfortunately, these inductive biases are not currently well understood, so this cannot serve as a basis for unification at present. The final possible type of explanatory unification we'll consider is as follows. Where previously we had to explain the success of multiple models, each acting in their own domains, a unified model can mean that we have one explanation for varied phenomena across multiple domains. However, it is not necessarily the case that having one unified model that is accurate in multiple domains facilitates having one explanation for its behavior in those multiple domains. This is because a unified model could just contain different, more or less independent mechanisms within it, each corresponding to a particular domain. This is the many models end of the spectrum in our diagram, which is taken from the Stanford Foundation Models Report. In the many models case, the unified model would still lead to multiple explanations for how it works, one for each domain. It would not help us understand deeper patterns underlying cross-domain success. The desired type of explanatory unification corresponds to the one model case in the diagram. In this case, the model works across multiple domains, but it does so by combining information from multiple domains within a single mechanism. In this case, the model would be a potential source of a unified explanation. In short, to know whether this type of unification holds in ML, we would need to know where our unified models fall on the one-to-many model spectrums. Currently, there is insufficient understanding of the mechanisms of multimodal transformers to answer this question. Now we turn to another possible epistemic benefit of unification that has been much discussed by philosophers of science: unification as parsimony. This line of thought argues that simpler theories are more likely to have various desirable properties such as truth, empirical support, and so on. For the sake of argument, let's assume this is indeed true of theories in the natural sciences. Our question then is whether similar arguments make it true of models in machine learning. We think there are a couple of reasons to be skeptical of this argument for the current wave of unification in machine learning. First, trends towards unification do not look like they are leading to simpler models, nor are the models that can perform well in multiple domains simpler in their mechanisms than more specific models. Unlike in the natural sciences, in machine learning, the degree of unification seems decoupled from complexity. A second reason to think that unification as parsimony doesn't work in machine learning is that many of the desirable properties that philosophers claim simpler theories have, such as greater likelihood of truth, are not straightforwardly applicable to the machine learning case. It is hard to say what it means for a machine learning model to be true. Furthermore, machine learning models are optimized only for predictive accuracy on a held-out test set. In contrast, scientific theories are optimized on a wider variety of criteria, truth being one of them. For these reasons, we think that it would take a lot more work to figure out a version of the unification as parsimony argument that would apply to machine learning as currently practiced. As we mentioned, many machine learning researchers are excited that they can now understand papers in other subfields of ML. A computer vision researcher is now more able to understand natural language processing papers if both papers use transformers. This capacity to share ideas due to a shared language is reminiscent of concepts of boundary objects and trading zones as used in science and technology studies. This facilitates collaboration, cross-fertilization of ideas, and other epistemically desirable activities enabled by this shared language. We think this is probably the strongest epistemic benefit of unification in machine learning. Now that we have discussed some potential epistemic benefits of unification in machine learning, we'll move on to discuss some epistemic risks. The first epistemic risk we want to highlight is that of further devaluing the knowledge of domain experts. Recall that with the advent of end-to-end learning, the need for domain expertise in feature engineering diminished. The advent of even more general models that work across multiple domains further devalues domain expertise. This poses some epistemic risks. Many high-profile failures in machine learning stem from the failure to properly incorporate domain expertise. A paper by Barocas et al. Names a similar risk the portability trap. To quote their description, failure to understand how repurposing algorithmic solutions designed for one social context may be misleading, inaccurate, or otherwise do harm when applied to a different context. Ignoring domain experts may not just be an epistemic risk. Later, we'll discuss how this also generates ethical risks. A second key ethical risk is path dependence. Enormous amounts of time have been invested into software infrastructure like TensorFlow and PyTorch. Researchers have carefully refined skills about training neural nets, developing intuitions for how to get them to work well. The volume of published findings about neural networks and the excitement around the area dwarfs that of any other subject in machine learning. This means that investigating other existing paradigms is structurally disincentivized. The lack of infrastructure means developing new models is more costly, the lack of intuition leads to a lack of ideas and frustrations in implementation, and the lack of excitement and new results means investments are unlikely to be rewarded. Put another way, the switching cost is extremely high. Additionally, the particular path that machine learning has gone down is in many senses arbitrary. It is the product of hardware lotteries and the ever-increasing availability of compute. Often, state-of-the-art methods published in top machine learning conferences fail to beat simple baselines. The combination of these two factors is known as path dependence. It implies a serious risk that machine learning research is not identifying the best possible learning methods. In the end, the only way to know whether alternative approaches to machine learning would be more effective would be to invest similar amounts of time and energy into those alternatives. To the extent that unification forecloses those investments, it represents an epistemic risk. A third category of epistemic risk stems from machine learning's epistemic spillovers, the epistemic benefits that machine learning methods offer when deployed in other sciences. Unification poses two risks in this sense. First, methodological triangulation is the process of using multiple methods to show that they give the same answer. This forms a more robust evidentiary basis. Second, it has been shown that diverse problem solvers can, in many settings, be more effective than a single highly effective problem solver. These two practices, methodological triangulation and the effectiveness of diverse problem solvers, mean that unification in machine learning can be inherently limiting for epistemic spillovers into other fields. A final epistemic risk we will discuss stemming from more unified models is the increased difficulty of understanding those models. Removing the need for feature engineering is supposed to be a benefit of end-to-end learning, but it can make the model harder to understand because the raw input features may be less intuitive to humans. More unified models can also be harder to understand to the extent that their unification consists in combining together information from different modalities in ways that are difficult to delineate. Those are some epistemic risks associated with increased blackboxing, and there are also attendant ethical risks. Having discussed these epistemic risks, we now move on to discuss the ethical risks and benefits of unification. The ethical benefits of unification in machine learning seem most likely to come from open sourcing ML models, as Hugging Face does. This is extremely similar to the open source model in the cybersecurity context. But the many eyeballs model of security is imperfect and can open up systemic risks, as happened in the Log4j vulnerability most recently. We think it is hard to say whether open sourcing large unified models is likely to be beneficial or detrimental. Here we will briefly outline a number of ethical risks that stem from unification. First, if machine learning systems as deployed are good for society, then those tools being worse than they could be implies an ethical issue. If, on the other hand, machine learning as deployed is detrimental to society, then those tools being suboptimal can be seen as a kind of ethical silver lining. Second, unification magnifies the tendency to ignore domain experts. In a similar way, it accelerates the tendency to ignore people from marginalized perspectives. Third, unification can accelerate the centralization of power in machine learning research and deployment by expanding the applicability of models over more and more domains of life. Fourth, unification implies a homogeneous model landscape, which can induce systematic arbitrariness in decision-making, a distinct kind of moral harm. Fourth, and finally, there could be negative impacts on aggregate social welfare if the models used by organizations to make decisions are more accurate but more homogeneous. In this talk, we have tried to summarize our arguments for the epistemic and ethical risks and benefits of unification in machine learning. In the process of constructing that summary, we have had to simplify and gloss over some points, and so we hope you will forgive that. If you're interested, we encourage you to look at the manuscript. Thank you so much for your attention.